Let me start thanking all the organizers, especially Alberto, Nazaré, and all of you for welcoming us and for making possible this nice meeting. I sent the title and abstract maybe after I have seen some titles in the program, and I took very gladly the invitation to join the club of people staring at diagrams, which I think it's a very good description of what I've been doing recently. Not understanding diagrams, but staring at them, right? That's the key word, I would say. Okay, so as Jesus said, I'm going to focus on diagrams whose points are now Banach lattices, and the arrows will be the morphisms, the lattice homomorphisms. So let me just briefly recall what do we mean by a Banach lattice, just in case. So we have a Banach space with its norm, and we also have a lattice operation. Well, we have an order. We can forget about it, actually, but the main thing is that we have two lattice operations, which allow us to define, given any 2 points in our space, the sup and inf, and now denoted like this, and these are also points in our space. And with these two, with these two lattice operations, we can define the absolute value as the sup of an element with x with minus x, and we require the norm to have the following monotonicity property. So every time we have that the absolute value of x is smaller than the absolute value of y, then the norm of x has to be smaller than the norm of y. Okay, so in this structure, or in this kind of spaces, we have different structures playing or interacting with each other. Well, I didn't say it, but of course the vector space structure is compatible with the order here. So I would say that if x is smaller than some y, then of course this forces x plus z to be smaller than y plus z for every set in my space, and also that lambda x is more than lambda y for every positive lambda scalar. So this makes compatibility between the linear vector space structure and the order. This is about the relation between the lattice structure and the norm or the geometry of our space. And a big part of the research in Banach lattices is precisely about understanding these relations, right? So how the geometry of the space, how the topology or the norm or geometrical properties of the space are related to lattice properties and vice versa. So, of course, the classical examples we would have are CFK spaces. So I've done my bit of CFK spaces for the day. Of course, LP mu spaces or any space with an unconditional basis also will have a natural lattice structure. So the idea is that this serves as a framework for many Banach spaces arising in classical analysis, function spaces mainly. And as I said, the morphisms we will be dealing with are the ones which preserve the operations we have now. So if x and y are Banach lattices, I will call T a lattice homomorphism if it is a linear map which also preserves the lattice operations, right? So it's linear, and I could say, for instance, T of the absolute value of x is the same as this, or equivalently that these things are served, things like that, right? So these are, once you assume linearity, these kind of conditions are equivalent. So in our mind, we have to remember that the morphisms, most of the morphisms I will be dealing with, I will require them to be lattice homomorphisms. Not always, right? No, not always. So, okay. So one of the things I have been more interested in is in the Banach space properties of Banach lattices, as I said, and one of the things that allowed us to go deeper in this relation is by means of the free Banach lattice generated by a Banach space. So I'm going to recall what this object is. So that will be our first diagram today. Well, my lecture at least. So given a Banach space, what is the free Banach lattice generated by this Banach space? So it's going to be the Banach lattice, of course, which I will denote like this. So it's a Banach lattice together with a linear isometry, which I will call delta, from E into certain subspace of this Banach lattice. So this is a linear embedding, isometric embedding. And I will require the following universal property. So if every time I have a bounded linear operator T into a Banach lattice, so E here is just a Banach space, but I have the property that every time I look at Banach, at operators into Banach lattices, I have to be able to extend them in a unique way to lattice homomorphisms. Okay, so there will be a unique lattice homomorphism, which makes this diagram commutative, right? So if I think of the copy of this Banach space sitting inside the free Banach lattice, I can think of it as an extension of this operator, and I get better properties of the operator, right? So it's somehow similar to the situation with Lipschitz free spaces, where you start on the ground level with Lipschitz maps, and you get linear maps, right? So I will comment some features about Lipschitz free spaces, because these work certainly as an inspiration for many for several questions in this work. So, well, the first thing I have to convince you is that such a creature exists, right? It's by no means obvious that this should exist, and actually, well, all this is partly based on joint work with Antonio Avilés and José Rodríguez, also from Murcia. And so we could not only prove that these spaces exist, but also provide an explicit description of them. So I'm going to give you an idea of how can we do that. So we can think of the following set of functions on the Banach space dual of E to the real line, and I'm going to consider these functions ordered pointwise, okay? And I'm going to give a specific norm for those functions. So I will take certain combinations, so it will be some sub of certain combinations of evaluations. Okay, so I have points in the dual satisfying certain condition. So I will look at, for every n, I can take n tuples of vectors in the dual space, in the dual Banach space I'm given with this property, right? This is, this is also called the weakly one-summing norm of this sequence of vectors. And actually, this is, you can think of it as, if you think of the operator from E to L1n mapping X to xi star of x, right? This is actually the norm of this operator, right? As an operator into little L1. So if you think of this space with the pointwise ordering and this norm, this is a Banach lattice. It's an exercise to check. And well, what is the free Banach lattice? Well, it's not exactly all these functions, but I have to look at some particular family of functions. I will look at the point evaluation. So for every point in E, I of course have the function delta of x acting here just by evaluating every functional at the point X. So these are linear maps, and their widths are continuous with respect to the right here. And if I look at this norm for those maps, it is very easy to see that they have exactly this property. So the free norm of this map in E, in the free Banach lattice of E, well, in this expression, I mean, it's going to be the same as the norm of X. And what we proved in this paper is that actually, if one looks at the lattice generated by those maps, deltas, inside of the space of all those functions, closed with respect to this norm. Okay, so if I take this set, this is exactly the free Banach lattice of it, meaning that this set here, this is a Banach lattice satisfying this universal property. Okay. So, as I said, this was done in 2018, or it was published in 2018, but maybe I should mention a couple of historical developments. Before that, there was actually a paper by Ben de Pachter and Tony Wickstead from 2015, I think, where a similar object was constructed. What they constructed was the free Banach lattice generated by a set. So it had a similar description, but actually it was just about having a Banach lattice with a certain set of generators which act as free generators, and you don't worry about capturing any linear structure as we do here, having this not only linear but actually Banach space structure. And well, they asked a bunch of questions about these spaces, and we started looking at this, and actually we could, in our terminology, we could actually figure out that these are exactly the free Banach lattice generated by L1 of the set A as a Banach space. And now the good thing is that with this description, we could tackle some of questions that were left open in the original paper by the Pachter and Wickstead, because they were, I mean, there was no explicit description of the norm, and certain questions about the norm then of course could not be easily dealt with. So it's actually, I would say, this combination of the diagrams, but by staring at the diagrams and also by looking at the specific way the elements of our space and the norm are described, that you can prove several things, I would say. Another development which was done by Antonio, Avilés, and José David Rodríguez Avellán was the construction of the free Banach lattice generated by a lattice. Now by a lattice I mean just no vector space structure here, so we just have a set with some lattice operations, sub and inf, and they could produce a similar creature. And also Gonzalo worked on Gonzalo Martinez Cervantes worked on projectivity properties of these spaces and identifying these as certain spaces of functions. All the things we have been doing are finding convex versions of these spaces. So in Banach lattice theory, there are these notions of convexity and concavity, which are certainly useful tools, and we could prove that one can define free P-convex Banach lattices. This was done jointly with Hector Jardón, Niels Clausen, Mitchell Taylor, and Vladimir Troitsky. And we have also developed complex versions of free Banach lattices. And this has been recently done with David de Hevia, who's speaking later, but not about this, myself. And well, I mean, this is just to give an idea of what we have been busy recently about these objects. Also, we have a recent memoir with Timur Oikber and Mitchell Taylor, Vladimir Troitsky, and myself, where we study several stability properties of this correspondence, right? So you can look at Banach space E and the free Banach lattice associated to it and try to understand what properties are preserved under this functor, if you want. So, well, if you're interested, I can spend some time on this at the end. But the thing I wanted to mention is how we can now use this to understand some of the problems. We can try to use this tool to try to understand some problems which originate in the relation between Banach spaces and Banach lattices. As I said, this is kind of a canonical object which you can, a Banach lattice that you can canonically associate to a Banach space. And one of the things I would like to mention is related to this complemented subspace problem, which, well, David will elaborate on this in the next talk, so I'm just recalling what this is about, but it's because the Banach lattice version of the result that well, one of the questions that Alberto has solved in his thesis. So let's take some time. Okay. So what is this problem? Complemented subspace problem for Banach lattices is just, well, as you can expect, you start with a Banach lattice, you look at the complemented subspace of it, and the question is whether this could be isomorphic to a Banach lattice, right? So whether you can put some lattice structure isomorphically in there, right? So this is the complemented subspace problem, and this is why I say this is somehow related to this object I mentioned before, because okay, if you want to show that a Banach lattice or that the Banach space is complemented in some Banach lattice, then well, you have to provide it with that lattice and also with the corresponding projection. The good thing about this canonical object is that if you know for some reason that your Banach space is complemented in some Banach lattice, then you can view it complemented in the free object. Okay, so this at least gives you, in principle, some intrinsic way, right, of understanding what does it mean that a Banach space is complemented in a Banach lattice. Because as I said before, this description of the free Banach lattice is purely intrinsic, right? I'm only using information from the space, right? I'm not looking at other space. Well, you could say, well, you're looking at L1N, but well, you agree with me that this definition is only just looking at the dual space somehow, right? That's what I mean. It's an intrinsic. You can use this to give an intrinsic characterization of what is that a Banach space is isomorphic to a complemented subspace of a Banach lattice, right? As I said, that the canonical copy inside the free Banach lattice is actually complemented. So in connection with this, one can do the following thing. So in principle, when one starts with a Banach space which happens to be a Banach lattice, of course, one can consider the corresponding free Banach lattice. And well, at first, one might think that there is some relation between the lattice structure you have here and the one you have there, but actually you cannot hope for that, because when you do this, the lattice structure of the original space is kind of forgotten, right? This map delta that I was telling you that embeds E into the corresponding free Banach lattice is just a linear isometry. It has nothing to do with the lattice structure of E, provided there were any, right? It's actually, the idea is that the image of this object inside of here, these elements behave as lattice-free objects, right? So there is no relation between delta of x and delta of y unless there was some linear relation between x and y, right? So you cannot hope for things for formulas like this to hold, unless they hold trivially in every Banach lattice, okay? So you cannot hope for those. But what happens when, as I said, what happens when E is a Banach lattice? Well, there is one particular map I could look at, which is the identity on E. And of course, because of the universal property, there must be some lattice homomorphism extending this map. And I will call this beta. Okay, so beta is a lattice homomorphism which has this property that it makes this diagram commutative. So a similar thing can be done in the case of Lipschitz free spaces. So if you start with X, I mean, you know, Lipschitz free spaces can be defined for metric spaces, for pointed metric spaces, but in particular, one could start with a Banach space and construct the free Lipschitz free Banach space over that. And again, if you look at the identity, well, I'm not sure whether I should be using the same letter here. Well, this is for the Lipschitz one. Okay. There is also some map, which is usually called the barycenter map. And in a paper, I forgot the year, Gilles Godefroy and Nigel.
It's a paper, I think that it's 2003.
2003. Okay, so Gilles Godefroy and Nigel Carlton studied 2003. Studied the question whether the map beta had a left inverse, right? A linear left inverse, right? So whether you, of course, in this setting, the map delta I'm writing here is just an isometry, but not linear at all. Actually, quite the opposite. And the question is whether, okay, you have this linear map beta, which maps the Lipschitz free space into a certain subset of it, and you would like to find out whether there is actually a linear embedding of this Banach space X into its corresponding Lipschitz free space, which commutes with this, right? Which has, like, I mean, if you take alpha and then beta, you recover the identity with a similar picture like this one, right? So in other words, when is the Banach space actually a complemented subspace of the corresponding Lipschitz free space? And in this paper, they prove that at least this happens, well, in several cases, in particular when X is separable. Several other cases, I think if you start with some free space of some space also, you have, well, if X is of the form f of y, right, for some y, you have this linear lifting, and actually this has several important consequences for the nonlinear geometry of Banach spaces. So we wondered whether a similar phenomenon could occur in our situation with lattices, right? So the thing we are looking at now is, okay, you start with a Banach lattice, and I can construct the free Banach lattice on top of that. Can I find a lattice homomorphism alpha, which makes again this commutative, right? So in other words, if E is a Banach lattice, is it possible, or when is it possible to view it as a sub-lattice of the corresponding free Banach lattice in such a way that this is also complemented? And we consider this in a paper with Antonio, Avilés, Gonzalo, Martínez Cervantes, and José Rodríguez. And we could prove that in particular if E has an unconditional basis, the answer is yes, right? The answer is yes in this case, or if it's, again, a free Banach lattice over some Banach space. And there are some obstructions, right? So also we could prove that it is a space of continuous functions, which is actually projective as a lattice, is the same, and So for at least for metrizable K, this is the same as being absolute neighborhood retracts. So if K is an absolute it's an absolute neighborhood retract, you get that the space of continuous functions on that compact space is has this property. Yeah. So let me see. I still have like what, like 10 minutes, 10 more minutes. Okay, so yeah, okay. So the last thing I want to mention, maybe it's another application of this free Banach lattice to construct one of the famous diagrams we were looking at this morning, which is the push-out, right? So free Banach lattices can be used to construct push-outs on free Banach of Banach lattices, and these have been useful to study injective objects in this in the category of Banach lattices. So let me recall maybe, well, I don't have to, well, I don't know. Let me just recall the pictures we had this morning. So I have, these are lattices, Banach lattices now, right? And the push out here would be everything, the arrows are lattice homomorphisms, as I said. And I want an object which allows me to complete this diagram, right? In a universal way, so that as Jesus was pointed out this morning, if I had another Banach lattice and maps which make this thing commutative, then necessarily there must be some linear map here making everything commutative, right? And you have some control on the norms. You can do this, you can do an isometric push-out diagram. And how would you do that? Okay, so once you have the free object associated to a Banach space, it's relatively straightforward, but let me just mention the way one can do that. So let us look at the push out of X of this diagram here. Let me call, say, G1 and G2 the corresponding embedding of each of X1 and X2 into the corresponding into the direct sum. Here I'm considering the direct sum with the norm, the sum of the norms in the sum, and I have several things I want. So I could look at the free Banach lattice generated by the sum, right? Where of course I have a copy of this guy, which I will call delta. And the thing I want is to make this embedding to respect the lattice operations both on X1 and X2 somehow, so that I can have S1 and S2 defined somewhere as, I mean, the idea is that this push out will be essentially a quotient, a lattice quotient of this free Banach lattice, okay? So I have to mod out by several things. So what are the things I want? Well, the things I would force S1, I mean, what would be S1? Sorry. So let us, instead of defining all the ingredients, let me just give you the idea. So what I want is to have some quotient of this guy, right? So that I will view the push out as the quotient of this Banach lattice under certain ideal. And in that ideal, what I will do is I will put everything so that the composition of this of the canonical embedding of X1 inside of the sum, and then this into its corresponding free Banach lattice becomes a lattice homomorphism. Okay, so I have to consider elements of the form what it would be maybe what delta of J of X, right, minus absolute value of delta J I of X, right? So that would be an absolute value here and an absolute value outside. So I would consider these elements, the collection of those elements with X in X1 or Xi actually, or I1, 2, which lie inside of this space. And I also want to make this commutative, so I have to consider well, the obvious thing, right? So I guess T1 and then this thing, G1 delta of X minus delta G2 of X for X in X0. And I consider the ideal generated by all these things. And actually one can prove that this proves out is exactly this quotient by this idea. Okay. And well, maybe I haven't given, I have not given much details about this, but one can use this to study injectivity. So what are the injective objects in this, in the Banach lattice category? Well, what do we mean by injective here? So we would mean that, I would say that a Banach lattice set is injective. Of course, if every time I have some lattice homomorphism into set and I view X as a sublattice of a larger Banach lattice Y, that I can extend this, and then I have some control on the norm of the extension. Well, actually, it is relatively easy to check that there are no injective objects. Banach lattices, right? Why is this? Well, actually, the key is that, well, remember first that what is the simple injective object we have in Banach spaces? The real line, right? Well, the real line, unfortunately, is not going to be, as a Banach lattice, is not going to be injective. Because one could think of the following situation. Imagine I take the real line here. I'm going to look at L1, an L1 space, say L1 and 0, 1, for instance. And I'm going to look at the embedding of the lattice generated by the constant functions. I mean, the constant functions, of course, they form a lattice, a sublattice of L1. And I can think of the identity here in the real line, which is, of course, a lattice homomorphism. If this guy were injective, I could extend it to a lattice homomorphism, a non-trivial lattice homomorphism. But this is impossible when, I mean, the existence of lattice homomorphisms from an L1 space is related to the existence of atoms in the measured space. Okay, so there's no way you could do that. So this is ruling out the possibility of having the real line as an injective Banach lattice. And actually, a modification of this argument allows you to conclude that if I had an injective lattice, right, and I had a map, and of course, I can think of an embedding of the real line in non-trivial injective object, a lattice homomorphism into here, and I again view this one-dimensional sublattice of an L1 space as the one generated by the constant functions. I'm always allowed to do this. And well, I could put here actually 0, 1, or I could put whatever measure space you want. So in particular, I could put 0, 1 to the kappa for any cardinal I would like to. And this would give me a lattice homomorphism between a non-trivial lattice homomorphism between L1 of this product and this space. And it is, well, it can be seen as a consequence of the Radon-Nikodym theorem that then necessarily the space set has to contain a sublattice isomorphic to this guy. And since I can do this for every kappa, well, I get a contradiction here, right? So there's no way I can have, I mean, in a certain way, the injective object would have to contain all these spaces for arbitrary kappa, and this is, of course, impossible. But this leaves open the door to having some bounded cardinality where you could still have injective objects. So one can wonder, what about the separably injective ones, right? So what about considering just separable light, right? So separably injective would be those where this space here is separable. And using the push out and an iteration, standard iteration process, we could prove that separably injective Banach lattice exists. And actually that, for instance, L1 of 0,1 to an uncountable product is actually separably injected. There are several others. And well, one can also show that there's no way you can have a separably injective Banach lattice. So necessarily they have to be non-separable, these objects. So, yeah. And yeah, maybe I think I should stop here. So thank you for your attention. Comments?
In the Lipschitz-free case, when you thank you. So in the Lipschitz-free case, when you don't have the lifting property, it gives you two Banach spaces which are Lipschitz isomorphic and not linearly isomorphic, just by a canonical diagram. It's easy. So in your case, where you, because now your map delta is linear, which is not the case in the Lipschitz frame, and you don't have the lattice lifting property. What does it give you? Does it give you two lattice structure on the same Banach space which are not equivalent? Or?
Well, no, because you don't know whether the complement is necessarily. Oh, no, wait a minute. Yeah, you would have, exactly. You would have like so in a situation when you start with a Banach lattice, right? Then, of course, the kernel of this map will be actually a lattice, right? It would be actually an ideal, right? And I can write the space somehow like this, right? Okay. So yes, I will have two. This will have a lattice. I mean, I can view this as the lattice structure given as disjoint things, which is completely different from the one I have here.
Okay.
Yeah.
That's interesting. Okay.
Yeah, but the thing, you know, I mean, when you have a Banach space which happens to be a Banach lattice, it is way easier to construct different lattice structures, right? So, for instance, you start with Hilbert spaces, and Hilbert spaces on an atomic. So the sequence, the L2 space sequences will be isomorphic or even isometric to the L2 of the unit interval, and as lattices they are, of course, not isomorphic.
That's right.
So
that's right.
Situation, the analogous.
You have also beautiful theorems by Nigel on all this. I mean, specific lattices, but you know this, of course. Thank you.
Thank you. Can I say something?
So you do this construction of the push out, which I would say is not the standard one, right? Because usually in the standard one, right, you simply take the direct sum of x1 plus x2 and quotient out the elements where the
You mean
maps,
standard? You mean Banach space?
yes, or Banach algebra or C-star algebra or whatever. Yes, so it seems to work in where the categories I'm familiar with at least, but it does not work for Banach lattices. Can you say why?
Yeah, that's a good point. Just make the sum of the Banach lattice.
the direct sum. Then the x and the y would be disjoint.
Yeah, they have to be disjoint, right? So
And
you
then-
could start with mappings which are not
But
preserving
you
this.
want to create like a free thing generated by the two that you start with. The Banach space of Banach algebra, this is just a direct sum. But here you make direct sum, you are forcing some disjointness. That should not happen in a free generated field.
Right, so I could think of some set where these two guys are not necessarily disjoint. So then there's no way I can force them to be disjoint, right? In a way. Yeah. Yes, of course.
The question. Paraphrasing Tom Waits, we are innocent when we paint. So, Banach spaces, lattices. Right? From here to here, you make your correspondence technically to fountain. Right? And by the way, let me call it empty. It's a forget. You have Banach lattice, forget the lattice, you have Banach space. These two things, by the properties you define, have all the look obeying what is called adjoint functors. This means that from here to here, so lattices maps from FBX into some Banach lattice is the same operator from X into the Banach space which is behind it. The exercise seems to be like this. If so, functors which have adjoint on the right respect limits by nature. This means that when you apply this to a limit, what you get is the limit of the things here. The push out is a limit, so the limit of the lattices you get should be the image of the Banach limit of the Banach push out of the things. So it's not the same. The push out is not the same as in Banach spaces. It's the free lattice associated to the push out of Banach spaces, more or less, I guess.
But it's not exactly that, right?
Should be the
It's not the free Banach lattice of the push out.
It's not. Should be.
Banach space. It's a Banach lattice. In the free Banach lattices, this is true.
What did you say?
If you take as to if you have a Banach space L1 and you construct the free Banach lattice, this is not the same object.
A much bigger order. Yes, way bigger. I mean, we can discuss this, but you have to mod out all the things, right? If you just take the free Banach lattice of the Banach space push out, there are, why do you have lattice embeddings, or why do you have lattice homomorphisms from to it's not clear to me. It's not completely clear. Or maybe you can do this, but the problem is that you cannot do then the isometric version, right? I'm not sure. Maybe Antonio has better insight.
Anything else? So 5 minutes?
Okay, thank you very much to Jesus and especially to the organizers and for the invitation and the planning of this conference. I'm going to talk about a counterexample to the complementary subspace problem in Banach lattices. This is part of joint work which is in progress with Gonzalo Martínez Cervantes, Alberto Salguero, and Pedro Tradacete. And actually, we haven't constructed a specific counterexample to the complementary subspace problem in Banach lattices. We have just proved that the sample constructed by Banach and Salguero is not isomorphic to a Banach lattice. Okay. I'm going to start by recalling the definition of a Banach lattice, which is a real Banach space equipped with a lattice order. That is, for any two elements, there exists a supremum and an infimum. The lattice order, okay, we have a Banach space and a lattice order. And this lattice order is compatible with the linear structure of X in the sense that if we have two elements, X and Y, in X, with X less or equal to Y, then AX is less or equal to AY for any positive A. And there is a compatibility condition with the norm, okay, which is expressed by this. If the modulus of X is smaller or equal to the modulus of Y, then the norm of X is smaller or equal to the norm of Y. Okay. The modulus of X is defined as the supremum of X and minus X. This is a Banach lattice. Okay. And the complementary subspace problem in Banach lattices is if are complementary subspace in Banach lattices isomorphic to Banach lattices. Okay. Let X be a Banach lattice and let E a Banach space complemented in the Banach lattices by a projection P. Okay. An important remark is that we are not assuming any compatibility condition between our projection and the lattice structure of X. Okay. For example, we can assume that our projection is a lattice homomorphism. That is, it preserves the supremum and infimum. Okay. But in that case, it would be a sublattice of our Banach lattice. Okay. If we assume that that the projection preserves the lattice operation, we are not assuming any compatibility condition. And for example, if we assume that the projection is positive, okay, positive is that it takes positive elements into positive elements of the image. Okay, then we could define the lattice operations in the image by this. The supremum of it would be this, the infimum and the modulus. And if we run E with this new norm, we obtain a Banach lattice. So if we start with a positive projection, for example, the image is isomorphic to a Banach lattice. But in the general case, we're not assuming any compatibility condition, as I said. These are examples. Okay. A reasonable starting point to think about this problem is to look at the known examples of Banach spaces which are not Banach lattices. Okay. For example, an example of Banach space which is not Banach lattices is the James space. Okay. Since for Banach lattices we have that if a Banach lattice doesn't contain isomorphic copies of little c0, then this Banach lattices has to be weakly sequentially complete. Okay. This was maybe a very well-known result in unconditional in spaces with unconditional basis, but this was generalized by Safiri into Banach lattices. Okay. James space that doesn't have copies of C0 because has finite cotype, for example, and it is weakly sequentially complete, so it cannot be a Banach lattice, isomorphic to Banach lattice. Another example is the Carlton-Peck space. Okay. This space hasn't the local unconditional structure in the sense of Gordon-Lewis. Okay. There is another notion of local unconditional structure of Dubinsky and Pelczynski and Rosenthal, but I think that the Gordon-Lewis notion of local unconditional structure is the usual. Is a Banach space has Gordon-Lewis local unconditional structure. If for every finite dimensional subspace of X, for every finite dimensional subspace of X, there is a space Y with unconditional basis. Such that the canonical inclusion of the space F into X, this is a finite dimensional subspace, as I said, can be factored through into this space. Okay. The canonical inclusion can be factored through Y. And this is uniformly bounded. This constant, the norm of the operator U, the norm of operator B, and the product, and the unconditional basis constant of Y is uniformly bounded, okay, for every finite dimensional subspace that you choose. This is the notion. This is a notion. And another example of a Banach space which is not isomorphic to a Banach lattice is the example constructed by Bowers and Morey of a Banach space which has not unconditional basic sequences because every Banach lattice has an unconditional basic sequence. An obstacle of this criteria is that they are also true for complementary subspace in Banach lattices. Okay, so these examples are not isomorphic to complementary subspace of Banach lattices either. Okay, and well, okay, free Banach lattices provide a criterion to distinguish between the two notions, to distinguish complementary subspace problems and space is isomorphic to Banach lattices, but it's not a very tractable criterion. A complementary subspace in a Banach lattices is equivalent that a Banach space is complementary in a Banach lattice to that this Banach space is complementary in its free Banach lattices. And it's equivalent that a Banach space is isomorphic to a Banach lattices if and only if there is an ideal containing the free Banach lattice of X such that the free Banach lattice of X can be decomposed into the sum of an ideal containing free and X, the canonical copy of X into the free Banach lattice. Okay. An ideal is okay. An ideal in a Banach lattice is a closed subspace such that if the modulus of X is smaller or equal to the modulus of Y for some Y in the ideal, then X also belongs to the ideal. This is the definition of ideal in a Banach lattice. And a nice property of the ideas is that they behave well under quotients, because if you consider the quotient of a Banach lattice an ideal, this is again a Banach lattice with the usual order and the usual norm in a quotient. Okay. And now I'm going to indicate some positive results about the complementary subspace problem. The first result is that every one complementary subspace of an LP space is an LP space isometrically. This is due to Bernau and Lacey. They generalized some previous results of Ando and Douglas for finite measure space. This is general. And an important conjecture is that every complementary subspace of capital L1 is isomorphic to little L1 or capital L1. This is an important conjecture. Another positive result is that every one complementary subspace of a separable C of K space is isomorphic to a C of K space. But again, we need contractive projections and separable. An important conjecture in the CK space setting is that every complementary subspace of C of the interval 0, 1 is isomorphic to a C of K space. And another important positive result is, but this is it's true only in the complex case, is that every one complementary subspace of a space with one unconditional basis also has one unconditional basis. This is due to Carlton and Wood. In the real case, this is false. The constant difference. You can construct examples in finite dimension in the real case. An important conjecture is every complementary subspace of a space with unconditional basis has unconditional basis. Okay. And recently, Banach and Alberto Salguero have constructed an example denoted by PS2 of a complementary subspace of a C of K space, which is not isomorphic to any C of K space. Okay. And this solves a long-standing conjecture also. Let's start with a first remark about the space of the Banach and Salguero. Its complement is in a CFK space, and hence it's an script L infinity space. Okay? Complement is a space of CFK spaces and script L infinity spaces. Okay, and a consequence of this fact is that if the space constructed by Alberto and Gregos were isomorphic to a Banach lattice, then it would be isomorphic to an A M space. A M space is a Banach lattice which has this property. The supremum of two positive elements in X coincide with the supremum of the norm of X and Y and the norm of Y. Okay. Whatever we have to assume that they are positive elements, okay, and we have this property. Examples of a sub-M space are the CFK spaces, for example. And Kakutani characterized these Banach lattices as the sublattices okay, space. Every abstract M space is lattice isometric to a sublattice of a CFK space. This is the most important property. Why? Okay, because if a Banach lattice is an Skipper-1 space, then it can be renowned to be an abstract L space. Okay. Abstract L space are Banach lattices which has this property. The norm is additive. Okay, this is a abstract L space property. And Kakutani, I'm not sure, characterize this Banach lattices as these Banach lattices with this property, the norm is additive, are lattice isometric to L1 spaces. Okay. I will only mention the idea. If you start with a Banach lattices with is an Skipper-1 space, you can define this norm. Okay. This is the finite sequence. Of finite sequence, and this is all the possible combination to decompose X into a finite sum of mutually disjoint elements. Okay. This is mutually disjoint elements. And applying Grothendieck inequality 2 times is not very easy. It's not trivial at all. You can check that this new norm is equivalent to the original norm, and the constant is this. I don't know if it's sharp, but in the two-dimensional case, this constant is sharp because, for example, little L1 in dimension 2 and little infinity 2 are isometric Banach spaces, but but any lattice isomorphism between these Banach lattices has constant greater or equal to 2, which is the Grothendieck constant in dimension 2, the square of the Grothendieck constant in dimension 2. And now, okay, this is the previous theorem. If you, now I'm going to say some consequence of this theorem. The first consequence is if X is a Banach lattice which is an script L infinity space, then is lattice isomorphic to an abstract M space. X, I'm going to sketch the proof. Since X is a Banach lattice, its dual is also a Banach lattice, and it's an script L1 space. The dual of an script L infinity space is an script L1 space. And by the previous theorem, the main theorem, the dual of X is lattice isomorphic to an L1 space. Okay. Then the dual is lattice isomorphic to a C of K space, okay, to L infinity, to a C of K space. And finally, since X, the canonical embedding of a Banach lattices into its dual is a lattice embedding. And this is lattice isomorphic to a C of K space, then X is lattice isomorphic to a sublattice of a C of K space. And a sublattice of a C of K space is an abstract M space by this characterization of Kakutani. Okay. Another consequence is that if X is a complementary subspace in an L1 space, which is isomorphic to a Banach lattice, then it is isomorphic to an L1 space. Okay. This is due to complementary subspace in an L1 space are a strip L1 space. Okay. Since it is complemented in an L1 space, it's a strip L1 space. It's a strip L1 space, and since it's also a Banach lattice, by the main theorem, X is isomorphic to an L1 space. Okay. And another consequence is this. if X is a separable complementary subspace in a C of K space, which is isomorphic to a Banach lattice, then it's isomorphic to a C of K space. Okay. Since X is complementary in a C of K space, it's an L-skip infinity space, which is isomorphic to a Banach lattice. Then it's isomorphic to an abstract M space. Okay. And in the separable case, abstract M space are isomorphic to C of K space, but only in the separable case. This is a result of Benjamin. And now I'm going to, well, okay. The example of the first remark that we can use to check that the sample of Alberto is not isomorphic to a Banach lattice is that we only need to check that it's not isomorphic to an abstract M space, which is more tractable. Okay. The criterion that they use to check that their space cannot be isomorphic to a C of K space is the following. Okay. A Banach space X is isomorphic to a C of K space if and only if there is a weak star closed subset A of the unit ball of X such that K is norming and the mapping delta X. Okay, I will write. The criterion is that there is a weak star compact, weak star close in the unit ball of X, such that this map first we can always consider this map, the evaluation. The canonical inclusion of X into its bidual, we can see this is an inclusion of X into the continuous the space of continuous function on the unit ball of the dual with the weak star topology. And when this map restricted to K is an isomorphism, the characterization says this, basically. The first condition, K is norming, is that this map is bounded below. And the second condition is that this map is surjective. Okay. So this is a characterization. This is an isomorphism. And abstract M space can be characterized in a similar way. Okay. Is that now we have the same mapping. The first condition says that this mapping is bounded below. Okay, bounded below. Equivalent to K is normal. And the second condition is that for every X, this function delta X restricted to the compact K exists the modulus of this one. The modulus with the pointwise order in this space. Okay. What is the meaning of this condition? Or we can say when we have this condition that the image of delta in this case is a sublattice because it's closed under modulus. So this is precisely the characterization of a characterization of a subm space, which is very similar to C of K space. And it's important because in their example, Alberto and Gregos, this is only an idea. They check that for some X in their space, for some X in their space, okay, the associative function to this X has no modulus. Okay. We can adapt their argument to the ASTAP-M space because they are taking a very nice function in this sense. They are taking a delta of something. So we can adapt their argument to ASTAP-M space. But this is only an idea. How much time? And a final remark is this. Recall that the counterexample constructed by Alberto and Gregos is one complemented in a C of K space with K scatter compact. Thus, the dual of this C of K space is a little L1 gamma space. So, the dual of their counterexample has also dual isometric to little L1. It's an important property. And its example, in addition, has a countable norming set. Okay. And this is an equivalent several statements that are equivalent. Okay. When we have an isomorphic dual of little L1 which has a countable norming set, to be isomorphic to a Banach lattice is equivalent to this, to be isomorphic to a sublattice of L infinity. So we can are always in terms of sequences, as Alberto Gregos did. And this is an sketch of the tool, but it's very easy to. I don't have much. I don't have time. Okay.
Thank you for the microphone. That could be a silly question because I'm not sure you mentioned Banach lattices which are script L1 or script L infinity spaces. What can you say, or can you say something about the script LP spaces which are isomorphic to Banach lattices?
As far as I know, I think that we cannot adapt this proof to script LP space.
I don't know personally, but why I ask the question is that it is known that you have omega 1 script LP spaces which are not isomorphic to each other, and they are all complemented in capital LP with speed different from 2, of course, but strictly between 1 and infinity. And it could provide other examples of complemented subspaces of Banach lattices which are not Banach lattices. I don't know if it has been done, but this is something to check maybe.
It's possible.
Well, okay, P equal 2 is a different story, of course, right?
Yes.
Of course.
Yes. Well, actually, it should be separable Banach lattices, but okay. First of all, thank you very much for letting me give this talk, and also for standing a little bit of problems that can perhaps in part I generated because of some chaos, and I think I forgot some of the few of the conversations we had about the organization of this thing. But you were very kind to deal with me with patience. So thank you very much. And I'm going to talk about compact spaces associated to separable Banach lattices. Okay, from these slides here, I have a few slides explaining what a Banach lattice is, but I think I don't need to go very much into this because of the previous talks, but I will just stop at this notion here, vector lattice, just to make this terminology clear. By vector lattice, I will mean vector space together with the lattice structure. It's just well, in Banach lattice we also have a norm, but if I forget about the norm, I get another structure which is a vector lattice, and this will be relevant at some point in my talk. Well, this was already commented, so I will go there directly. I will remind another. Well, it was also kind of mentioned, but I will be a little bit more detailed here. What is an ideal of a Banach lattice? It's well, some subset which is a vector subspace, and also whenever I have a function, for example, if I have a positive function, I have all the positive functions that are below, or more generally also to integrate non-positive function. Whenever I have a function f in my ideal, any function which in modulus is dominated by f has to be also in the ideal. This is actually the same as to say that you are the kernel of some linear and lattice homomorphism. And notice also that here I don't demand when I say ideal that this y is closed. Sometimes people would make this assumption, but for me ideal simply doesn't have to be closed topologically. Just actually this makes sense in a vector lattice, as I said before. And what is the principal ideal generated by a vector? Well, as usual, it's just the smaller ideal that contains that vector, which I can actually describe in this way. It's the set of all elements in my Banach lattice, which are dominated by a positive multiple of the of x, or of the absolute value of x. So, for example, just to get an example that I wrote there, if you start with this Banach lattice, the lattice of integrable functions, and I look at the function that I call there 1 is the constant function equal to 1. What is the Banach? The ideal generated by the Banach by the constant function 1? These are all the functions of L infinitus of bigger 1 that are below a multiple, scalar multiple of the constant function equal to 1. Those are not dominated by a constant function, and these are just the bounded functions. So actually, here formally, I mean, I can take this is a subset here. If I forget about the normal, just as a subset, and as a subset, this is the principal ideal generated by 1. I could write it like this, but there the terminology that I use is to use the Banach lattice in which I am working and putting the generator as a subindex. So that's a principal ideal notion. And this is an interesting thing that I found out when I was trying to, well, I'm now working with these Banach lattices, but I'm not quite an expert, so I try to learn from time to time. And I found this, and as a kind of person who comes from rather from topology, this caught my attention, this fact. Whenever you take a Banach lattice and you take a vector and you look at this principal ideal, this you get, and you look at it as a vector lattice, so you forget about the norm. This is always a CK space. A CK vector, C of K is a vector lattice. You just look at the linear operations and the sub-inf, you forget about the norm. That's a vector lattice. And the principal ideals of a Banach lattice are always a lattice isomorphic to a C of K. Moreover, to a unique C of K, because there is a Banach stone theorem in here, that if you have C of K is vector lattice isomorphic to C of L, then K must be homomorphic to L. So actually, each time I have a Banach lattice and a vector, this uniquely determines a C of K, actually uniquely determines a K. So this is a way to associate compact spaces to vectors in Banach lattices. Okay, so this is a very nice theorem. I'm going to do the following. I'm going to use this notation. So each time I have a vector lattice E and a vector X, so I have this compact space K, which I will call K sub X of E. So I have this association of vectors in Banach lattices to compact spaces. Actually, we could even forget about the vector, because one can prove that if you take two vectors whose principal ideal are dense in the Banach lattice, they always generate the same K. So if I look at vectors that somehow generate the whole Banach lattice, I'm not going to change the compact space. So this means that whenever I have a Banach lattice, and this is whenever I have a Banach lattice that is generated by just one vector, in the sense that the ideal generated by a vector is dense, then I have a unique compact space associated to it. And this is the case, for instance, of every separable Banach lattice. So in that way, given a Banach lattice, I can associate in a unique and canonical way a compact space. And I may wonder what are those compact spaces? So the first the first example, the most natural one is, okay, start with the Banach lattice, which is itself a C of K. What do I obtain? What do I obtain if I start with a C of K and I take the constant one function, for instance, as I said before, what is the ideal generated by the constant one function? It's all the continuous functions that are dominated by a constant one. But these are all of them, because this is bias theorem. This is every continuous function is bounded. So actually, this is the full C of K, and that means that the compact space associated to C of K is K, which of course this is natural. And this means that I have all compact spaces I can imagine. I can represent them as the compact spaces of some lattice. Okay, good. But as you know, there are some people that we do not kind of accept them in our clubs, that some clubs have been defined this morning, that there are some people who believe that only separable Banach spaces exist, or only separable Banach lattices perhaps are worth. Okay, so let's give them this definition. Let's let them for a while into our club, and let them give the following definition. I'm going to call a compact space SIC if it is the compact space associated to a separable Banach lattice, to the most natural class, just the separable Banach lattices. Okay, it's a little bit, as the referee claimed, the flamboyant name, but it kind of makes sense. SI is from separable ideal, S is from separable, I is from ideal, and CK, I don't have to explain in this conference. Okay, so let's look at what are the compact spaces that appear in this way from separable Banach lattices. So what is this class of compact spaces? And this was the method of investigation in the work I'm presenting here, but by the way, it was written in the first slide, but I didn't mention its joint work with Gonzalo Martínez Cervantes, with Pedro Tradacete, and with Abraham Rueda. Okay. So what compact spaces are SIC? So let's, well, and this question one can interpret as saying, how, when you look at separable Banach lattices, what vector lattices can be represented as separable Banach lattices? Indeed, it's not exactly the same because this compacta really represents the principal ideal, but it's very close to that kind of question, to this question actually. If I give you a vector lattice, when I will be able to make it a separable Banach lattice? The compact spaces tell me how the principal ideals have to be, which is clearly a necessary condition and very close to sufficient. Okay, so here is the first, this is the same example I wrote here, but if I'm only allowed to use separable Banach lattices, then the separable C of K are the metrizable K. So the first observation is that metrizable compact spaces are SIC. Okay. So next thing that one could do, okay, perhaps I could start with C of K, but instead of using the constant function equal to 1, I could use here some other function. I could use here some function f, and I could look at what is the ideal generated by a function f. So these are all the continuous functions that are somehow dominated by a multiple of f. Well, actually this can be described as a set of all functions of the form f multiplied by a function which is continuous and bounded on the, let's call it support, so it's not exactly the support, on the subset of K where f doesn't vanish. So you look at where the function doesn't vanish, put a bounded and continuous function there, this is an open set, put a continuous and bounded function on that open set, and then multiplying this by f, I will get all the principal ideal. But then it means that the structure of this thing is the structure of the continuous and bounded functions here. But continuous and bounded functions are the same as continuous functions on the Stone-Check compactification. So I represented this ideal as a vector lattice as the continuous functions on this compact space. So the conclusion is that, and I have what SIC compacta I got here, the Stone-Check compactifications of open subsets of metric space. So if I had taken an open subset of a metric space, like for instance a unit interval, its Stone-Check compactification will be SIC. Or also beta n is SIC, because the natural numbers are also an open set in the compact metric space in a convergent sequence. For instance, I remove the limit and I get the natural numbers. So we have metrizable spaces, we have beta n in our class, and here we can go back to the first example I wrote here, big L1. So big L1 is also a separable Banach lattice. We get big L infinity, which is a CK, as it must be by this general theorem. But what is the K to this C of K? This is, well, if you don't know what it is, you can just take it as a definition. This is the Stone space of the Lebesgue measure algebra. I mean, if you want, just the K whose CK is big L infinity. So this guy we also have to put it in our list of sequence. So we have metrizable spaces, we have beta n, and we have this Stone space of the measure algebra. Okay, and here are some properties about subspaces and quotients, but I'm going to skip this kind of. Okay, so once we have examples, next thing, okay, this is like I have my class here. I want to understand what this class of SIC spaces is. So I found a few people here. So it's like I have a lower bound on the class. I have some things that I know that they are there. Let's try to get some upper bound on the class. Let me try to understand what is not there. Let's exclude people. So the first thing, well, okay, is that if you think of what all these examples have in common, it's that they admit a strictly positive measure. Measure, I mean always I have a compact space measure, I mean a Borel measure, not measure defined or a regular Borel measure defined on the Borel sigma algebra regularity property. And strictly positive means that it's positive, it's strictly positive on every open set, non-empty open set. And this is actually quite a common condition in topology. I mean, it's a well-known class of compact spaces that admit a strictly positive measure. And of course, metrizable have this property. Beta n has these properties. I just may put some measure on the isolated points. And the stone space of the measure algebra has a positive measure basically by definition, by its very nature. But this positive measure has some further properties. It is of countable type. This means, being of countable type, that if you make the integrable functions over that measure, you obtain a separable space. This L1 mu is the L1 of 0, 1 is the separable L1 mu. This is what countable type means. And moreover, it has some property that it's perhaps not, or at least we didn't find in the literature such notion, that we can call analytic. It means that, okay, I have my measure on K, so I have the continuous functions on K, but every continuous, if my measure is a regular Borel measure, all the continuous functions are integrable. So C of K lies in here. I have the integrable functions over this measure, and I have C of K in here. If my measure is of countable type, this is a separable Banach space. This is a separable, this is a Polish space. So, and if I have a subset, so if you remember Godefroy's talk, we can wonder how good this subset is. It could be a Borel set, but I may remind that, so we have Borel sets, and we have arbitrary sets, but they have a nice class here called analytic sets that Gilles defined this morning, that we can call as continuous images, which this can be characterized as continuous images of the bare space or of a Polish space. And what we can say here is that the continuous functions are an analytic subset of the integrable functions of this measure. And I can call this measure analytic. So this is telling me somehow that C of K is kind of definable, it's kind of nice, it's kind of not an arbitrary, it is not of set, it's not that much of set theoretic nature, but of descriptive set theoretic nature. Well, the fact that my compact space admits the strictly positive measure, this is not difficult to prove. I mean, our C of K has to be represented with a separable Banach lattice, and then elements in the dual corresponds to measure on my K because of the representation theorem. And if you are separable, well, for each point on a dense set, I can find an element in the dual that norms it. So I have like countably many measures, but I can join them together. I have one measure, and well, you do some exercise to prove these two things, which are not surprising since our class comes from the class of separable Banach lattices, which are all Polish spaces. This is a kind of a very, from the descriptive point of view, very natural thing. So it's to be expected that our spaces are somehow definable. Okay, now, but when you look at this kind of theorem here, this actually reminds a lot of a different class of compact spaces, which is that of Rosenthal compact spaces. They were mentioned at least in Alberto's dissertation. I'm not going to find them actually. I'm going to give you an alternative definition in the next. It will appear on the screen. But the theorem about this class is that every measure in a Rosenthal compact space is of countable type and is also analytic according to this definition here. Well, this theorem, as I stated there, at least as far as I know, it's not stated like that anywhere, I think. But just because the people were not using this definition, so they were not stating it. But somehow, if you, the fact that every measure in a Rosenthal compact space of countable type was something that was first claimed by Bourgain, but he didn't provide, or at least didn't publish, or it's not, we don't know of his proof of that. And it was proved later by Todorchevich. And the fact that it will be analytic, this is, if you combine this Todorchevich theorem with or the first work that I'm going to mention now, you get the statement that I wrote above. And here I'm going to write another statement because this is, the difference between these two theorems here about Rosenthal and about our C compacta is in our C we claim there is one such nice measure, while for Rosenthal we say all of them are nice. And this is an important difference. But sometimes we have for all theorems for our class as well. I mean, somehow the fact that our class has to be nicely definable is going to reflect sometimes in an arbitrary way or more general, not arbitrary. So for instance, we have this theorem I wrote below. If we have a sequence of G delta points, this means points that have a countable basis of neighborhoods. In a C compactum, then I can represent C of K. Here I represented C of K inside a space of measures. Here I'm representing C of K inside the metric space R to the n, this product, simply by taking a function and evaluating it at this sequence of points. And then I claim that this representation here is also an analytic representation. I get an analytic subset of R to the n. And this will happen all the time I pick a sequence of G delta points. But I cannot put arbitrary. Actually, if I take beta n, for beta n, it will work very nicely if these are isolated points. But if I put an ultra filter, then I will get something which is not measurable and they will not get analytic. And the theorem of Gilles that is similar for Rosenthal compacta is that, well, in Rosenthal compacta, you don't need to restrict to G delta points. This is true all the time. And it's actually, in the case of separable Rosenthal compacta, which is actually what we should perhaps restrict to, it's a characterization. A Rosenthal compactum is you can characterize it by the first theorem as those compact spaces as that whenever I represent C of K in this evaluation way, I get an analytic set. So it's like the C of K is always nice whenever I try to represent it on a sequence of points. Okay. So after these things, so what is the thing? We have a class that somehow seems to look like Rosenthal compacta, but on the other hand, we know, at least we know that it should be larger because it includes things like beta n or this compact space of the measure algebra, which are very far away from Rosenthal. Rosenthal compacta have a property that they are full of convergent sequences. Every sequence has a convergent subsequence. For instance, if they are full of convergent sequences, while beta n has no convergent sequence. So beta n is not Rosenthal, but is sick. And well, our first conjectures when we had this kind of statements were that perhaps there was some relation between Rosenthal and our class. And actually we thought that perhaps every separable Rosenthal compactum was going to be a particular case of C compact. This was our first guess. But this is actually quite far from truth. I'm going to write here another theorem we have in our work, which says that if I have a compact space which is sick, then we can construct a tower, a countable tower, a sequence, increasing sequence of closed metric subspaces, of compact metric subspaces, such that whenever I take a sequence of points that is escaping from the tower, so that xn is not in Mn or xi is not in Mi, then that sequence is equivalent to the basis of beta n. Its closure looks like beta n. So this is telling me that there are a lot of, well, one possible case of this tower is that it's just the full K. I mean, that K is metrizable itself. It would satisfy this let's say, trivial tower, everybody's K. But if that is not the case and the tower is not trivial, then this is telling me that there is a lot of copies of beta n in my space. So in particular, this excludes all Rosenthal compacta which are not. Well, here I wrote it's more or less how do you find these sets Mn, but well, this is perhaps a little bit technical for the talk to understand. So as a corollary of the above, one gets that actually in a SIG compactum, if you take a closed subset, it's either metrizable or it might contain a copy of beta n, because if it's not metrizable, it will escape from this tower over time. So I will be able to construct such a sequence which will give me beta n. So the picture that we have after this is that what we have is that I could draw here some big class that I can call CK analytic. These are all the compact spaces whose C of K can be viewed as an analytic set. For instance, an analytic set inside the space of Bezier. We have this nice Bezier I wrote before. In here, we have this well-known and studied class of Rosenthal compacta. And we had also our SIG compacta. But actually, these classes are kind of orthogonal. The only common ground are the metrizable. The only common elements are the metrizable, which for us in this context is like the trivial ones, so the small ones. Well, one could think also if perhaps this characterizes somehow if the Rosenthal are the nice, which are full of convergent sequences, and the SIG are the nice ones which are full of beta n. Well, it's actually not the case either. For instance, actually from this theorem, you can exclude beta n times beta n. Beta n times beta n is not SIG. You cannot construct a tower of metrizable spaces as above. It requires a little bit of exercise, but if you construct such a tower like that, you will be able to always to find points xn that escape from the towers, and the closure will be beta n times beta n, which is known that it's not homomorphic to beta n. Okay, so while we have this, so it's somehow this SIG, they are sitting somewhere between must be nice and must be, let me call it like that, full of beta n's. Still well defined somehow in this context. Beta n is a natural thing because it's the compact space that gives me L infinity, which is nice because these are just the bounded sequence. This is very well nicely defined. Okay, so well, once we have this, somehow, of course, the goal here would be: can I find a characterization of this class? Can I find some internal topological characterization, some test that tells me these compact spaces live, these others do not? Unfortunately, we don't have such a characterization so far. This is a problem for us to have a efficient way to know whether some compact space is SIG or is not SIG. Some medical tests, let's call it like that. So next thing, okay, let's look at some class of examples that may look like kind of interesting. So the next thing that we did is, okay, let's look at the following. Takes a Boolean algebra, an algebra of subset of n that contains a finite set. So, well, if you are familiar with Stone duality, you can somehow analyze compact spaces by, or an important class of compact spaces, the zero-dimensional ones, by looking at Boolean algebras, and in particular, subalgebras of P of n correspond to separable compact spaces that are moreover completely disconnected. And we have the following theorem that I'm going to write here. If we have a subalgebra of the subset of N, subalgebra here means that algebra means that it's closed under finite unions, intersections, and complements on the Boolean operations. Then B is the algebra, is isomorphic as an algebra. Isomorphism algebra means preservation of the finite unions and finite intersections and complements. B is the Boolean algebra, if the Boolean algebra of Kloppen's of a sig compactum, if and only if I can find a disjoint sequence of positive vectors, not written here, but these are positive vectors, in some separable Banach lattice, in such a way that my algebra B is the set of subsequences that have a supremum. So what is this telling me? This is a different way. So my initial setting of the problem that we were studying was I can associate to Banach lattices compact spaces by looking at the principal ideal. Now I have a different way of analyzing which separable Banach lattices can exist. I'm taking disjoint sequences and I'm looking what subsequences have a supremum. So certain algebras we should be able to represent them as the suprema of a certain disjoint sequence. Others we could not. If I remove here separable, this could be arbitrary actually. I could take any algebra. But if I take separable, which are those? And actually this is the same as finding the sig compacta that as finding what algebras are the Kloppen sets of sig compacta. Okay, so what can I say about this? Well, so this is a different way of studying sig compacta of this specific class. So what further remarks I can make here? So first of all, if I have an algebra like this, if I have a disjoint sequence of vectors in a Banach lattice, well, I didn't write that, but also I should say that those vectors are uniformly bounded. I mean, they are. Let's say they are normalized, or all of norm 1. Then, well, if you have disjoint vectors, I can always, if I have my disjoint vectors, disjoint positive vectors, and I take scalars that are summable, then I can always produce this vector here. This is general Banach space theory. But actually, in this case, if these are disjoint vectors, this sum coincides with the supremum of, yes, this sum, sorry, because I made a mistake. I said we are going to suppose that everybody has norm 1. This is complete error. It's not what I want. Okay, so what I want is actually, I don't know what the norms are. Yes, so in this case, sorry, so forget about the scalars. What I know is that if these vectors have summable norms, then the series is also convergent because every non-convergent sequence is convergent. But actually, if these are disjoint vectors, this is the same as the supremum of the guys in a Banach lattice. So this so in this sequence here, they will have some norms, and if I take a subsequence, and this subsequence is of summable norms, then the supremum has to exist. So this means that this algebra B must contain what is called the ideal of summable sequences of the sequence of norms. Actually, what I was saying was very wrong, because this B becomes trivial if I mean the norms have to tend to 0 if I want the non-trivial B. Okay, so let's take sequences that the norm of Xn goes to 0. So this means that I have a lot of guys in my algebra all the time, because if I have a sequence that goes to 0, there are a lot of subsequences that are summable. So one thing is that whenever I have the Klopen algebra of a C compactum in this way, this algebra has to be quite big. It has to contain all the summable subsequences of a sequence that scalar that goes to 0. And well, this is perhaps a little bit difficult to read. This orthogonal means all the subsets whose finite intersection with, all the subsets that the intersection with every element of B is finite. Okay, so here orthogonal, typically orthogonal, you think of scalars, but here instead of scalar multiplication, what I'm doing is intersection. And instead of 0, I put finite, and this is my meaning of my orthogonal. So, so because of this thing here, A has finite intersection with every element of B, if and only if the sequence of norms in the subsequence A doesn't accumulate at 0. This is okay. This is rephrasing the thing which I have above. And okay, as a general thing, if I have an algebra like this and I take all the subsets that are entirely in B's and every subset still belongs to B, its orthogonal has to be a countably generated idea. Whatever this countably generated idea of subsets of omega just means that there are countably many sets that every element. I can describe that family as the sets that are contained in some elements of a sequence of sets. Anyway, okay, perhaps for those which are not familiar with this kind of terminology, I will just put here a corollary, which is, I wrote before that beta n times beta n is not sick. Now I'm writing that beta n times the counter set is neither sick. And this actually does not follow from the previous theorem. We could not know it just from the previous theorem. We actually need to use this property that if I take the Klopen sets in here, and I look at the hereditary sets, and I look at the orthogonal, that is not countably generated. And that is why beta n times the counter set is not sick. Actually, we conjecture that if a product of two compact spaces is sick, it is because the two factors are metrizable. But we don't have a proof of that. We have just proofs of some cases like this one. Okay. So this is like perhaps a little bit more technical than the other, but it allows us to, discard some other candidates to be sick, but they're not sick. Okay. It's 6:30 when I have to finish, if I remember correctly. Well, actually, I was talking about ideals, and I have a definition here. Sorry, perhaps it should be before. Anyway, let me just, because it is here, I can remind it perhaps more quietly. So a family of subsets of P of n is an ideal if it is hereditary. I mean, if you have a set in the ideal, all subsets must be as well. It's closed under finite unions. And that should be just the definition of ideals, but well, we are always interested in ideals that contains the family of finite sets. So I'm going to put it in my definition just to say ideal. I mean ideal that contains all finite sets. Okay. So once I have an ideal, I can associate to it an algebra of sets, which is I take the ideal and I take all the complements of elements in my ideal. For instance, if my ideals are the finite sets, my algebra will be the finite set plus the cofinite set. But then they form an algebra, because if I stay with the ideal, I don't have, it's not closed and the complements that I want from an algebra. If I add the complements, then it becomes closed under all the operations. So, okay, as I said, because we want somehow to have a better understanding of this class, and we still don't have something very handable, okay, we focus on some classes, and then we wonder which Boolean algebras or which algebras of sets of this form are the algebras of the C compactum, or in other terms, by the previous definition, when an algebra of this form can be the subsequences of a disjoint sequence in a separable Banach lattice that have a supremum, because these algebras that have this property are those that correspond to the set of subsequences that have a supremum in a separable Banach lattice. Okay. So Well, there are some class of here. What this was related to some class of ideals that are called non-pathological analytic p-ideals. They rise in work of Ilias Farah, some different subject. That's a definition, but perhaps it's not worth that we try to read now this definition because it's a little bit technical, but it's just to give you a flavor of what this is about. You start with a set of finitely supported sequences that are of positive numbers that are summable. And then with them, you look at, well, all subsets of n, such that whenever I start taking q's of my sequence and summing the elements of in here in those q's, and I take supreme over all sequences in my C, then the limit goes to 0. Okay, this is, as I said, you need to sit a little bit for a while to understand that, but just this idea that can be represented in a certain way. So I will not try to give idea of that definition, but let me put a couple of examples. Well, of course, it's called analytic. I mean, from this definition, people who know the discrete set theory will immediately see that this is an analytic definition, but I give you as an information, every such ideal will be an analytic subset of the subset of n. But for instance, the following are of this form, non-pathological and analytic p-ideal. The summable ideal, this is what I said before. If I have a sequence that goes to 0, and I look at the subsequences which are summable, that's a non-pathological p-ideal, as it's written above. Which is actually quite closely related to our problems here. Another one is the density 0 ideal. So it's like you take a subset of n, and for each n you measure what proportion of the numbers up to n you put in your set, and you take limits, and if that limit is 0, then you call that set of density 0. It's very natural to call this thing density. For instance, if you think of the even numbers, this would be 1/2, because up to n you have half of the sets in your set. But you want something that is not half nor set, you want this to go to 0. So if you take, I don't know, powers of 2, this will have density 0, because the proportion of powers of 2 that you get as you grow is this time very small, less and less. Okay, so these two ideals are non-pathological analytic p-ideals, and this is like, after the list of examples that we wrote at the beginning, this is like one non-trivial example. Something kind of complicated things that we know that are sick. If we take a non-pathological analytic p-ideal, for instance, any of the two that I wrote before, then the corresponding algebra BA will be the algebra of Cloppen's-Ogesic compact. Actually, the algebra of Cloppen's-Ogesic stone space. If you don't know what a stone space is, it's just a space whose Clopens are the algebra I wrote. So actually, this is based on a theorem of Piotr Borodulin-Ajeya and Barnabas Farkas, and which is also, this statement is written in the paper by these first two authors, but it's also based, the results also based on a previous work of the same two authors plus Banach that has been mentioned a number of times here already, and where they actually already found this class of non-pathological analytic p-ideals. I think the word analytic perhaps should be here, sorry. When they analyzed this, a problem that is very similar to the one I'm trying to analyze here, which is they work on Banach spaces, not Banach lattices. And they work with unconditional basis. And they ask the following. Given an unconditional basis, look at the subsequences of my unconditional basis that I can sum the vectors of the... So a certain family of subsequences you will be able to sum and get the vector in your space. this is easy to see that it is an ideal, actually an analytic ideal. But the question is, what are the ideals that can be represented in this way? For which ideals there is an unconditional basis such that exactly the subsets of that ideal are those where I can sum my basis. And the answer was that this is exactly a non-pathological PID. Okay, so their problem is quite close to ours, although not that, but with some differences, because an unconditional basis is also a Banach lattice. And if I have an unconditional basis and I create from it a Banach lattice, the sums of the basis is the same as the suprema of the basis. The difference is that, well, we were interested not in ideals but in algebras. So we were assuming that our sequences already have a supremum in order to have the total set inside. But you could consider that a technical thing of how to name the things. And also, our question is more general because, I mean, my Banach lattice doesn't have to be a Banach lattice with unconditional basis. Actually, the disjoint sequence may form an unconditional basis, but my separable Banach lattice might have more things. For instance, I could start with an infinity, take the basis, the standard basis of C0 inside an infinity, but I could add also the characteristic functions of the even numbers and create the Banach lattice with that. And then I will have an unconditional basis. I will have that I can sum every, if I look at that space, it will not be the same that in fact that I can sum, this space will not be the Banach lattice associated to the unconditional basis because I have guys which are not in the Banach space and made by this. So it is like more general question. But, well, we can prove the theorem. We said we don't have a characterization. Our theorem was that we know that if it is non-pathological, we can construct a Banach lattice like this, but we don't know about the converse. And the construction basically is, we take essentially the same construction of theirs. We just add something on top in order to get our supremum. It's like procedure similar to, you start with C0, you add C. So here you start with their examples and we add some extra supreme of the whole sequence to get into the same context that we were. And that is our Banach lattice. Okay. So it's 6:22. It seems that I think this is my last slide. It's still like 7 minutes, but I think nobody will complain if we finish here. We have perhaps some questions. So let me finish here. Thank you very much. Questions, comments?
Yes, very nice work. That's my favorite object here, you know, but very nice work. I assume that you have examples of analytic CK in your original definition for the embedding into L1 of mu, which are analytic non-Borel, probably.
In this, well, for that, I would guess you should go here. I should have a look at this non-pathological analytic P ideals if there are there analytic non-Borel, because we don't have many explicit constructions, so I would actually be dependent on this. So I should have to look at this theory.
Actually, we are not, and it's interesting because we are closing the circle with this morning's lecture. We are in the vicinity of what I talked about this morning, because if you have an ideal and you consider all the complements, this is of course a filter. And if you take a filter which contains a Fresnel filter and is analytic, then the collection of full sequences which tends to 0 with respect to that filter is an analytic, weak star analytics of space of an infinity,
Yes.
which is not isomorphic to an infinity.
Mhm.
So we are kind of relating
Yes,
with
yes.
the problem I asked this morning. So that's very interesting.
Yes, the problem, I mean, the kind of things that we know, of course, it's natural to think that if you take for instance, some ideal here that is still analytic, but and large, you could get to one of the sick compacta.
Mhm.
But actually, this is quite difficult to prove it is actually sick. And this is actually the only case where we can have it. So actually to produce things of high complexity, you need to put some like analytic non-Borel ideal there and produce from it a compact space or an algebra. But yes, we are.
Also, you are in the vicinity of those representable spaces. So,
Yes.
but you show actually something better. I mean, the representability tells you that it's Rosenthal compact or contains beta n, but actually what you have is better. I mean, you have this tower of metrizable.
Yes, exactly. Somehow,
spaces,
yes.
so-
Perhaps I should have. Yes, I should have referred to this. I mean that if we, yes, if we stay inseparable compacta, this analytic this representable Banach
Yes,
spaces
but-
that from
but-
your work and Talagram.
Yes, but you have better anyway. I mean, you have better without using it.
It's like the big circle here is corresponds to the work of
Yes.
yours and Talagram or representable space.
Okay, thank you, Antonio. Who wants? Microphone.